Mm-hmm.
Oh, perfect. For posterity. My main objective today is to actually run through a data set and show you how to use FORC-PCA using FORCNL, which is a software that is used by a lot of people to process forks, but you can also use it to run this algorithm of unmixing forks. It is in Igor, which unfortunately, you have to pay for. But I think students can benefit from greatly reduced prices. Not that I'm advertising. I think it should be somehow open software, but this is what we have now. So we're gonna go ahead. Yeah, so that is my main objective, to show you how to do it practically. And there's a file online that you can download and use and follow along if you wish, but it's not necessary. But before that, I'm just going to go a little bit into the background. So FORC-PCA is unmixing a first-order reversal curve data sets using principal component analysis, as the name suggests, of course. So basically, you go to location, core, you measure a bunch of forks, you get your fork data set, and then you reduce those 2D maps to this kind of data set where each sample is reconstructed as a data point within this principal component unmixing space. And so the ultimate goal is to actually describe each of these data points as a linear combination of n members. So that's in short what FORC-PCA is. So why do we want to unmix? Because we're interested, of course, in quantification of magnetic components in geologic materials. And this is important for a lot of reasons. I'm just listing a few here. You want to understand how different magnetic minerals form, or you want to study sedimentology of some formations, biogeochemical processes in the grand scheme of environmental change. So a lot of these applications are used in environmental magnetism, but not only. Then the next question is, well, why forks? Why spend a lot of time in the lab, like Ramon showed, setting up measurements, collecting data, collecting a lot of these forks for, let's say, one core or one locality, and spending a lot of time dealing with processing and everything, and not focus, let's say, on bulk measurements or curves, single curves. And the answer is because forks, as you see in this diagram, give you sort of a two-dimensional view of magnetic signatures in the sample. So forks are 2D magnetic characterization tools, as Egli has mentioned in his review paper from 2021, and they provide a map of diagnostic signatures. Okay, and then when you unmix, you get results that are less ambiguous than when you just use single curves or even bulk data. Forks are not a cure for all, but they're very useful in many situations. And finally, why use PCA to do the unmixing? So principal component analysis is a multivariate statistical technique that analyzes data sets for which observations are described by several intercorrelated variables. In our case, our observations are the actual points or dots in the diagram, or the points on the forks themselves, and the intercorrelated variables are the pairs of BCB which describe these observations. And so you take this and reduce it and represent this data set as a linear combination of a new set of variables that are orthogonal, and these are called the principal components. And the principal component analysis captures natural modes of variability in your data sets. So one of the advantages is it's fairly objective. And as I said here, basically just what I said. This is the score plot, so-called score plot that PCA produces. In this case, the variability in this particular data set is described by the first two principal components, but you can have just one principal component describing most of the variability in your data set, in which case your unmixing space is a line. So for that line, you can just pick 2 points at the end of the line, which will act as your n members. And we'll see, and in this case, we have a plane. But before that, another advantage of PCA is that the data can be reduced to a low rank approximation that is relatively free of noise. So basically for each point, you can reconstruct the fork. It's not going to be the same as your actual measurement because you're just reconstructing it based on the principal components that you are using in your analysis. So in this case, the first 2 principal components are used to reconstruct the fork that arrow is pointing to. And if you were to use more principal components, you would sort of add in a lot more information, and that information a lot of time contains most of the noise that you gather. So that's why I'm saying that it's relatively free of noise because you're just using these first 2, in this case, principal components, so a low rank approximation. And so as we'll see, and as we'll explore this unmixing space with the cursor in FORC-NEL, you can move around the unmixing space, and at every point you'll have an instantaneous reproduction of what the fork diagram looks like and the fork. So in areas where you don't have a lot of data, you can sort of predict what some of these fork diagrams might look like.
Okay.
Yes.
What do you mean by mixing space? You mean the linear combination space?
Yeah.
PC? Okay.
Yeah. Unfortunately, the way I set this up is we'll go to the actual software afterwards, and I'll show you exactly. But it is that space essentially the score plot. So using that predictive power, you can also estimate what your n members might look like. So in this case, we have 2 principal components describing a plane. So you will have 3 n members necessary to describe that plane and enclose data. And what you want to do is use the smallest triangle possible to sort of contain your data. And the vertices of that triangle or simplex will be your n members. And so you have their location, you have the reconstructed fork diagrams. And one thing that you want to be looking at is, are these n members realistic or physically realistic? Do they actually look like real forks that you might measure? And that's what Ramon was saying about, you want data points to be sort of close to your n members so that they are described fairly well. If you notice this n member 3 is kind of far away from the data points. And if you look at this and you have some experience with collecting forks, you might say, well, it doesn't quite look right because maybe there's a negative area here that is not looking realistic. But in this case, since we don't have data points close to that vertex, the top one over there, this is the best we can do with this version. So this is all, what I'm showing you right now is basically the original paper that we published in 2015, in which one of the problems that we kind of left for the future was, how to actually choose these n members in a way that they are physically realistic. Of course, you can move away from the data and choose n members that are farther away, but you have to sort of have some kind of other information for that. The other thing was this linear additivity of the n members. So is this satisfied? And does anybody want to chime in and say if this might be happening or not? Anybody who's used it? Are you?
The assumption is that the n members are fixed in all samples.
Yeah, exactly. And the other thing that we're doing here, we're doing the PCA directly on the fork diagrams. And so not all the processes are captured in the fork diagrams. For example, reversible processes. Okay, so we knew going into this that we had to do more work, but we went ahead and published this method. and then came back 3 years later with an improved algorithm for unmixing using FORC-PCA, in which the two improvements were addressing this linear additivity issue and coming up with metrics more objective for determining physically realistic end members than just user experience. So for this paper, we actually had mixtures of two different end members in which we knew how much of each end member was in there. And we had a series of these. We had multi-domain, single-domain mixtures, and you can see here some of the fork diagrams of these mixtures. The single-domain one was a MV1 culture, so magnetofossils or magnetosomes, magnetotactic bacteria products. We had a mixture of SD and sort of a PSD sample, mostly characterized by multi-vortex particles, 1 to 3 microns in size, and then a vortex MD series of mixtures. So in short, using the 2015 method, so these here down here are the known mass fractions that were put in each of these mixtures, and using the 2015 method, you notice that it's not a linear relationship between the two, okay? And this is, again, because using just a fork diagram to do the PCA, you're omitting a lot of the reversible processes that are contributing to the total magnetization. So the solution is to apply the PCA to the actual magnetization, to the actual forks, rather than the fork diagrams or the fork distribution. But this approach poses a challenge when you're actually exploring interactively the unmixing space with the cursor and Igor, because you are getting the reconstructed forks, but then you would have to process the forks to get a fork diagram. That would take time. So in practice, the solution was to apply PCA on the magnetization surface fit, so that polynomial. And there's a set of 6 coefficients that the PCA is applied to. So by doing that, using that methodology, and then comparing to the known mass fraction that went in each of these mixtures, or the series of mixtures actually, because each data point is one sample, the relationship is not perfect, but it approaches this one-to-one linear relationship. And then the second issue was coming up with metrics for determining of your end member, if your end members are physically realistic. So the 3 criteria were saturation of the forks. So M over MS never exceeds 1, and they saturate. Monotonicity, so the forks increase monotonically, meaning their first derivative is never going to be negative. And then determining if the forks themselves cross or intersect. And each of these feasibility metrics, has a value of 1, where it's perfect. And you can use them in combination. You can use 1 of them, 2 of them, 3 of them, and you multiply each other. And then you can plot contours on top of the unmixing space. And we'll see how to do that. The 4th metric for physically realistic end members is positivity of the fork diagram signal. So as we've seen in single domain, in the samples dominated by single domain, a lot of single domain particles, you'll have these negative regions that are going to be there. But in some cases, you don't necessarily have negative signal in the fork diagram. So then this metric checks for anomalous negative areas, which may appear if you go too far away from the data set and you start subtracting signals and creating these artificial negative areas. But this metric should be used separately, not together with the other 3. One thing that I really want to stress out right here is that these physical reality metrics should not be used to triage your data. So I've seen this where people take their fork data set, and instead of carefully combing through each fork and making sure that it's well processed and there's not garbage looking forks entering the analysis. All the data is dumped into the PCA. You do a rapid analysis so you can get to the physical reality metrics part, and then use those to sort of identify outliers and eliminate them from your data set. So this is not why this particular function was created. So please do not try to use it this way, because you'll end up getting rid of more of the data that you can actually use, for one. And then, yeah, garbage in, garbage out. So your analysis will not be optimal. All right, so having said that, before we go to, Courtney is wide-eyed. Before we go to our practical demonstration, are there any questions or any comments or additions? We are going to try to reproduce this figure from Courtney's 2021 paper in paleoceanography. Any questions so far? Yes.
Just really quick, just to clarify. So you mentioned like multiple specimens. Is this like the equivalent of like one site, or is this like a whole like formation you're looking at, or? Yeah. Depends
what your analysis. Ideally, you want it to be in the same stratigraphic sequence or in the same locality, but you can also mix different localities if the end members you think are the same. So yeah. Another thing, okay, we'll get to that, but
is there a minimum number of data points?
That's a good question. So this particular data set, I've chosen because it contains 65 forks, so a sufficient number to sort of get a statistical analysis that is valid. But no, we've gone down to 10 samples or even less for identified end members. So yeah, the more the better, and the more data you have, the more you'll cover the end mixing space, and you'll see that this simplex will start it's going to be very intuitive where the end members will be when you have data that covers your whole mixing space. So yeah, Max.
I have a stupid question. What if you only have 2 contributions?
2 end members?
Yes.
You will basically, you will hope that your PC1, so the first eigenvector, is controlling the most of the variability in the data set. Yeah, and then you don't need to go to, yeah. Okay, so here's the data set. It's in Igor. Let me get rid of this for now.
I just have a follow-up question to the Max's.
Yeah.
Which is just sort of evaluating the significance of the difference of some of those end numbers, right? Because you're going to have more variability explained by PC1. So you sort of see this in this data set, right? That
right.
end member 2 and 3, which are the same in PC1, the differentiating PC2 sort of look much more similar to one another, right? So I guess I'm just curious in terms of like thinking about the significance of the difference of those end members versus breaking it down.
Right, and it depends if your end member, if 2 end members are sort of along the horizontal, along PC1, or they go more along PC2, and PC1 is kind of going in between one end member and the mix of the others. So that depends on how the data kind of spreads. Is that not answering your question?
No, that's
okay.
I mean, it's just sort of slightly by definition, you're going to have more variability along PC1 such that there will, yeah.
Right.
Will have.
Yeah, so we'll see actually what happens with this particular data set. And so right now we're looking at the 65 forks that Courtney collected from Wilson Lake, New Jersey. So it's a section from the PETM, the Paleocene Eocene Thermal Maximum. And a nice thing about this data set is that you can use PCA to sort of separate out different magnetofossil populations. So these are magnetofossil-rich sediments, and we are able to sort of pull out using FORC-PCA different types of magnetofossil morphologies that give different coercivities. So the first step, it should be sort of what you would normally do, where you collect the data and you bring it into FORC-NL and you process and you prepare everything for the PCA, including doing the slope correction and normalizing for PCA over here. That's very important to have. And then, you know, subtract the lower branch, get rid of that first point if you need it, correct drift, everything. So everything should be prepared, your forks smooth, find the optimal smoothing factors and all that stuff. Okay, so once you have that, you have to be on the actual data with this cursor, which you can move with the mouse, and select all your forks. Right, so I selected all the forks in the data browser. And then you go to this menu, fork EM. EM goes from end members, or, you know, stands for environmental magnetism if you want. And there's a PCA analysis panel. So once you click on that, you will see that in the data browser over here, you have a results folder at the bottom, and it's already selected, so you're good to go. In this panel, the first thing that you will do is select the PCA grid. And this grid is essentially the area on the fork diagram that you want to actually focus on. So we'll see, we press on this, and the data here, the actual numbers are Tesla. So you go on the BU or HU axis. Let's go from 0.08, let's say, to 0.04. That's 40 millitesla. And then on the horizontal axis of the fork diagram, we'll go from 0 to 140 millitesla. And the resolution here is 1 millitesla. So by the time you get to this step, you already know how your fork diagrams look like. And ideally, you want to measure all your diagrams on the same measurement parameters, but it doesn't have to be like that because this grid resamples the data. But you do want to have coverage. So you don't want to sample outside of areas that do not exist in some fork diagrams.
So with the resolution there, you recommend that the areas could be the same or whatever, but the increment your fields step should be the same when you're doing your fork.
Yeah. I mean, I would try to stick to similar steps and similar parameters. Yeah, but you're right. If you do like 5 millitesla increment versus 1 millitesla increment, then that's going to be a difference in the fork diagram. So the PCA might think, okay, these are different end members, when in fact they're same but smooth differently. Or right, Rob.
Let's say you measure a bunch of parts through HC like 120, HC maximum, and measure, I'm missing some stuff. To the next batch of parts out to 150. Would you constrain this PCA grid to your lowest coercivity value? Yeah, I would. Yeah, I would. Yeah.
Rich Harrison wants you to be sure that you've actually selected all of the data before you run.
Yeah, it's selected and it's run. And once the results folder is created, I don't think you have to select all the data. You just work on the results folder.
Excellent. I'm just relaying Rich's message to you.
Thank you, Rich. I'm glad you're here. Okay, so continue. Oh, maybe he was right. Okay, sorry about that, Rich. Let's close this one. And just to be sure, I'm gonna delete everything and redo because we don't want to run into problems. Okay, here we go. Right, okay. So going to go back, PCA analysis panel, PCA grid.
He wants you to know that he feels vindicated.
Yeah, I'm sure. He's actually controlling my hands. All right, so here's our grid again. Continue. Oh yeah, now it's going through all of them. You were right. Okay, so it doesn't show anything, but the next thing to do, we have your grid, we're going to run the PCA. So this button here is actually applying the PCA to that fit to the magnetization surface. And the first thing that it's showing us is a scree plot. And on the x-axis is PC, on the y is the the variance explained by each one, and then cumulative in blue. So if we look at this one, the first principal component explains almost 70% of the data, the variability in the data set, and then the second principal component explains another 17 or so. So we're going to go in this case with the first two principal components. And if there's time at the end, I can show you what happens if you just choose the first principal component. If you consider that the third principal component also explains a significant amount of the variability, then you can do that, and then you're operating in 3D space. So you'll have 4 end members that it's a little bit harder to visualize and actually move around and explore the unmixing space, but it can be done. But in this case, starting at the third principal component and going to fourth, fifth, and sixth, there's sort of incremental decrease. So the first two principal components explain most of the variability in the data. And the difference between those two and the other is large enough that I'm comfortable going with the first two. So the next thing to do is select these first two and do plot PCs. All right, so several things happen here. You are getting a fork diagram, you're getting the forks, and you're getting this score plot with all 65 data points contained in here. And I'm gonna just zoom in right now a little bit. Okay. So this is a space that we will explore interactively. You see there's a cursor here. I'm going to drag it to this area. You can move it with the mouse or with the arrows. If you press Shift and move the cursor with the arrows, it moves faster. And one thing that you'll see that is happening is the fork diagram is the reconstructed fork diagram at the cursor location, and it's going to update instantaneously as we move around. So I'm just going to do it by the color, right? So the color of these points is right now random, but you can actually recolor them to represent depth and core, for example, or anything else that you want, or you can have them the same color. This is just a choice of the programming in this case. If you look back to Courtney's figure, in this case, the really light ones are the down core sample, and as you get dark, you go up core. So this is something that users can choose how to represent the data and how to color the points. Okay, so as we move in this space, as we move to this end of PC1, you'll see that you have sort of typical magnetofossil signature in marine sediments or lake sediments with a central ridge and some of this background, the negative area. And as we move to the other end of PC1, I'm not going to do it, but I could plot the central ridge distribution of coercivities, and you'll see that it actually is going from having its maximum around 20 or 30 all the way to over 100. So the main variability in the data set is described by this change in the central ridge, the maximum coercivity, going from a component that is biogenic soft to a component that is represented by biogenic needles in this case, in this particular case. And as we move, so I'm going to go into the middle here, as we move up and down PC2, you'll have to believe me. Actually, you don't have to believe me. I'm going to go back here. But you'll see that this end member here contains a biogenic hard component that as you move along PC2, you will gain or lose it. So this bump in this curve will become more prominent or not. So the second PC actually explains the variability in the data set, or is due to, as you move along it, is due to this biogenic hard component, which is magnetofossils that are more elongated. Conventional magnetofossils, not giant. Okay, so the next step is we're going to choose our n members. So in this case, as I'm looking at the distribution of data points, I feel like I can, contain the data into a triangle like that. So let's just do a rough. Okay, we're just going to say n member 1 is over there, and go to the menu and open this n members panel, define n members panel. So you move with the cursor to where you think n member 1 is, and you set it, and then go to n member 2, which is probably here, and you can see the fork diagram looks like that typical magnetofossil rich sample. Set EM2, click on that, and then the third one probably over here somewhere. Set EM3. Right? Once you've set those, you can calculate the proportions, and a bunch of things happen. You will see the actual n-member fork diagrams, and this time series of the actual proportions. So up here are the fork diagrams of n-member 1, n-member 2, n-member 3. Let's move this, or let's make it a bit smaller. So we can, okay, so yes. What changes in these n-member fork diagrams is just the colors. You don't actually change the fork diagram. This remains the one that you will use to explore the space. Okay, so we have the n-member fork diagrams, we have the n-member forks right here. And then in this window, n-member 1, 2, and 3 plotted as a function of sample number right now. So, but each sample, you can translate it to depth or age or whatever. So you have a time series going from, in this case, from old to young. But it matters how you arrange your data in FORC-NL. Okay. Any questions so far? We're getting close here. I hope I'm not forgetting anything. Yes.
So you've got the data, quite a few data that's sitting outside.
Good point. Yes. So we did a rough and ready setting of the n members. And now that the triangle, the simplex is drawn, you want to adjust. And some points may be outliers, or some maybe will remain outside of the analysis if your n members. So let's say, let's go to, okay, somewhere over here. n member 1, let's put it over here. Already you see the fork diagram contains all these anomalous negative regions. Let's go zoom out a little bit and set the n members here. So we set them, calculate, and then, right, all the data points are in here, but it seems like the n members themselves are sort of farther away, and we'll use the physical reality metrics to constrain this a little bit. But by just looking at the fork diagrams of, let's say, n member 1 has that negative area here that does not look physically realistic. So we know we're kind of far out when we selected that particular point. So just going to go back in and adjust a little bit. So n member, this is 3. I want to be consistent. And so I was just choosing n member 1 to be this one, and member 2 this one. You can mix them around, but you'll lose track. So better be consistent. Okay, so this sort of analysis contains all the data points, or sort of, you can make adjustments to it. You can, play with it and see, what the proportions look like. But it seems like none of these proportions are negative in this case. So we'll just stick with this for now. And the last thing is to do the physical reality metrics. Okay. And I have a little time for that. Okay, so back to the FORC menu physical reality metrics. And this is sort of a thing that I do every time. I kind of go through all these fields because sometimes it doesn't work if you just say do it. I'm gonna basically go through all of these fields and change them, or enter or whatever. But in this case, this number here this 50,000 has to do with the numbers here on the axis of the score plot. So I'm gonna shrink a little bit. So I have more of this area. And I know that in this case, my data set, you know, I'm gonna do the, okay, let's see. Instead of 50,000, I'll put 70,000. And that'll go to, oh, here, yeah, 7,000. Look at this axis. So 70,000 here, 70,000 here, resolution of 20. And I'm going to use all three of these: saturation, crossing, and monotonicity. Say do it. Takes a few seconds. A resolution of 10 will give you a speedier analysis, but then the contours will be a little bit more jagged, as you'll see. Any questions in the meantime?
Yeah, I mean, how do you define this limit? I mean, they are wider than with respect to
yeah, I define them based on the fact that I played with the data set a lot and I noticed where these contours are. And so you can also see, so okay, so I'm gonna go here now and just look at this area. Oh, sorry.
I mean, that's experience.
Yeah, yeah. You want at least to have the whole data set within these. So you could go to 30,000. You know, you want all your data to be in there. But in this case, the contours are way out there. So I wanted to have a bigger area to see. So yeah, something like that. If you go to 80,000, you'll get coverage of this part too. But you don't actually need it. So this contour here is the 0.99. So practically all of these end members that we have in here are physically realistic according to these three metrics that we used: the saturation, crossing, and monotonicity. But as we've seen, as you go kind of away on this side, it doesn't look physically realistic. So in this case, it might be useful to actually use the fourth one, the positivity. So I'm going to go and use just that and see what kind of contours does that parameter show us. But as a rule of thumb, I try not to go too far away from the data. As you've seen, the data kind of itself organized in a way that you can pick out that triangle. I mean, you can play with it and have it in a way that there's not so much white space here. It's sort of, in a way, subjective, the way you choose the end members, but you know, that's one of the shortcomings.
Hi.
Hello.
Why do you not run all four? Is that a computational thing?
Not necessarily, not a computational thing, but I think if you run all four, the positivity will take over and sort of be the main weight in the whole calculation. So it's recommended not to do that and just use the first three together, or just two of them, or one, depending on, I mean, in some cases you will have forks crossing each other, that's inevitable, and that's why you don't need to, you know, you can have values less than one because of.
So the fact that using the first three metrics doesn't identify some unrelated features of E and 2 is due to the fact that the matrix applies to the entire Fock space. And so on average, it is good, but then you have some spots where it is not good. Is that the reason why the contours are not spotting this problem?
In some cases, the contours will spot the problem. In this case, I am not sure. Maybe Dave Heslop can chime in on this issue of the feasibility metrics and why they don't capture sort of. I mean, you can also do a cutoff and say maybe 99.99. That's arbitrary, right? So 0.99 is you know, a too low of a number, so you have to go to 0.999.
measures for that.
Right.
So given that these are real measurements, as Grant showed this morning, overall, then maybe 95% is high, but the remaining 5% is just noise.
Right. 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 And we went to the positivity just because those contours were the 0.99 contour was so large that now it seems like maybe this contour over here will tell you, well, maybe if you go past this, they become physically unrealistic. So this one kind of helps.
Just suggesting you try out for it once and see what happens. Give you some give you the reference.
Can you just also summarize Dave's answer, because people may have not heard that online?
So
You're earning your money.
all right, so Dave was saying that sometimes using the example of monotonicity, it's not necessarily to go all the way to 1, but you can have 95% of it, be fine and to explain that. And sometimes, maybe in this case, you have to go actually higher or closer to 1 to actually constrain those contours. And it's helpful to have these metrics, but it's not necessarily a cure-all. Did I see a hand? Yeah, I'm gonna run all these.
Reality metrics to help us set the triangle.
Can you repeat that?
Okay,
all right, let me actually. I'm not doing a good job being MC.
You showed us that we can play a bit on how to set the 3 end members.
Mm-hmm.
And does it make sense to run first these model metrics before setting the end members to see what's realistic?
Oh, yes. I see your point now. Right, so I basically set the end members and then I ran that. And the question was, should we run these first and then set the end members? I'm not sure what's going to happen if you run these first before actually calculating the proportion. So it may be just a way the software works, that you have to first run the first calculation of the end members and then do the, but maybe Rich can chime in. We can try it, see if it crashes or not. But that is, yeah, absolutely valid. Especially if you don't have experience, just, why not use that kind of guide before you actually run the analysis. So I think this run, yeah, combining all 4 of them kind of did this, which resembles what the positivity metric showed us. So that's why I'm saying this, it seems like the weight of the positivity took over on this one. I think that's what's happening, unless something else. Rich has any other ideas, but anyway.
No, in this example, you're pointing out that you have unrealistic negative regions up to on the left-hand side of your diagram, but the end member 1 there is in a pretty okay region.
Yeah, end member 1 is okay, end member 2 is okay. End member 3 seems to be.
Is that the one with the negative areas?
But end member 3, should have negative areas. So,
okay.
Yeah, like I said, I mean, these are guides and they're trying to make your analysis more rigorous, but in the end, it still kind of relies a bit on common sense and your experience. But I think the rule of thumb is, try to choose the smallest simplex possible that encompasses all your data. The risk you run into here is that your end members will be mixtures of components. So they won't be pure if you get really close to the data, and those data points that are close to the end member are not pure end members, but are combinations themselves. Does that make sense? Okay. Yeah, I think I'm at the end here. My last slide was basically sort of a summary of all the steps I've done. And either this talk is online, or you can pause the YouTube video and use these particular milestones to run your analysis. And yeah, I'm happy to answer more questions in the time we have. So thank you. Yeah, go ahead.
Say that you can use an arbitrary color coding for the points representing the individual sample. My question is if you can, for instance, color code your sample according to the percentage of signal that is reproduced by your end member. So to see if there are samples where more of the signal is not represented actually by these end members.
Yeah, I think you can, but you would have to create a new wave in which you establish some kind of scale, let's say, that goes from 0 to 1 or whatever, and then assign a color or a size of the data point to represent that scale. Hey, Bruce.
Does this work for them folks?
It's a good question. I'm not sure exactly that it works for REM forks the way they measure them in Australia. Probably they do, but I can tell you that we have just submitted a paper on nonlinear Triage diagrams doing unmixing. So that is essentially that REM fork space, but measured in a different way. So you don't measure the fork diagram and subtract, all the other regions. You just measure the area in between the diagonals, that remnants, using the Nathan Church's method, nonlinear Triage diagrams. So we've achieved that not using FORCNL, but MATLAB, but it works. So did you have a comment, Andrew?
Running. So the export code that's used to calculate conventional REN fork I-fork diagrams that I showed you this morning is done off in a regular measurement grid. And one of the challenges of integrating that with conventional measurements is which code out there will process the data. So at the moment, the unmixing algorithms deal with uniformly spaced data sets.
Yeah.
It sounds like a nonlinear Triage approach is a welcome step forward for getting the remnants forward and unmixing it. But in terms of, as you said, the Australian version, the problem is the irregular measurements versus the regular.
Yeah, and the nonlinear Triage diagrams are also measured on a quasi-logarithmic scale, so irregular. Is there a particular reason you asked the question, Bruce? Okay. Well, we did it because we were trying to explain the coercivity components from IRM acquisition curves or DMAC curves. So we needed an equivalent type of map, so not a fork map, but a remnants map.
So kind of.
Oh, you go. Please just I'll talk over you with this microphone.
Yeah. So I've never used this the PCA before, so forgive me if yes. But just so that I understand it correctly, when all said and done, you calculate the 3 M numbers and you use the IRM unmixing analogy, would it be proper to say that each of those N numbers are in a perfect world represent like 3 different phases of which all these samples are composed of different proportions. So, okay, so also building off the IRM unmixing, would it also be say that these 3 N numbers, they're not like idealized, there's a, just be really simple, there's an FC magnetite, a PSC, and an MD. It's not so much that, it's that these represent a distribution of different forks that all kind of more or less are idealized by this N number, and then you're kind of doing that variation with between that?
Yeah, thank you for that question. So, if your data set contains forks that are dominated by one N member, that's your ideal case. Then your N members from the analysis will be very close to a pure N member. But if, let's say, along your core or whatever, you just go from, you have mixtures of 2 or 3 N members, but you never get close to pure N members, then your N members will end up being, mixtures of components, and it's not the ideal case, but that's what we work with. Unless you can supervise the analysis somehow by putting in forks that represent the N members you have.
And then, so how do you also, so how do you also address the fact? So, with the previous presentation where you can have the same fork that are caused by very different phases, like how is that kind of accounted for with the calculation of N numbers?
Which fork?
So, like for example, you have the multiple vortices, and you're like, oh, this one can cause this fork, and all 3 forks look very similar, but they're all caused by
Yeah, I mean, if they're really the same, then you can't separate them. But if they differ and you have enough of them and a mix of them to sort of cover the mixing space, then maybe you'll be able to. That's my distance. You want to add anything?
Well, but even the natural component has some degree of variability. So the problem is, what does an N member represent? Maybe you can imagine better like a fog, and you hope that the fog is well condensed, but it's not necessarily the case.
Okay.
Yeah, so actually kind of have a comment that follows on nicely from your question. I think that really all the N members are parts of the fork diagram that co-vary together. So there's no reason that an N member has to be a pure mineral, a single domain state, any of these things. It's just looking for parts that co-vary. So even if you don't have, or you're getting N members that are mixtures just because of the how big you've made that mixing space, it could be in reality that your N members are actually mixtures. So if just as a very simple case, imagine some magnetic mineral is being blown into the ocean that is then causing the formation of magnetotactic bacteria. Those things will always co-vary together. So you see that detrital component and that magnetofossil component in the same N member, and they're genetically linked to each other. So it's pulling out genetically linked N members rather than pure minerals or pure domain states or things. So hopefully that actually helps you interpret the process rather than simply saying that's magnetite, that's hematite.
Yeah, especially if you're after the process that generates your assemblage. Anybody else?
This is maybe a silly question, but if you know like the processes that are in play in your sample, can you set more than 3 N members of this? Like, can you say there's like 5 different processes that we think are happening?
I mean, if you're operating in, let's say, in unmixing space defined by 2 principal components, having an additional N member, so a 4th or a 5th, I think over characterizes. You don't need it. You don't need it unless you go to higher PC space. This multidimensional, sometimes hard to visualize. Well, always hard to visualize beyond your 3D sort of human beyond the 3D.
You need like the number of PC components plus 1 to define a region in that space.
Yeah.
If you know that there's more processes at play, would that help you or would it not give you any?
That might be useful. I mean, it's always useful to know, but usually you hunt for the process. You're trying to figure out what's going on, or trying to find the N members from a mixture. If you have additional information, maybe PCA is not needed, or this kind of unmixing is not needed, or but I haven't seen any examples of that. But thank you. Good question.
Okay.
All right, I think we've reached the point where we need to take a little bit of a break. So we're going to take a 15-minute break and start again at 1:15 here. During that 15-minute break,